Okay, we'll restart. So um, just to confirm that I checked that the reference by Bernard Burrs, and it was written that Descartes indeed examined the sheep eyes and then found this inversion and also aberration of the optics in the eye. So until then, like the 1600s or so, humans didn't know about this kind of fact. Probably many people assume that we are seeing the world in as it is, not upside down in the back of the eye, and also there was no aberration of the image, probably. Okay. So then about the phobia, and then one of the things about the phobia that we probably don't know until you are told is that there is no blue cones in the central phobia, which is a bit hard to believe. I think that's probably hard to believe. Has anybody heard of this fact that we don't have a blue cone or a blue sort of white wavelength receptor in the phobia? So this is the so the schematic of the foveal cone receptors. It's not really appropriate to show this kind of figure because none of the cones are colored like this way. Okay, all of them do not have any color, but their sensitivity, maximum sensitivity, is indicated by this figure by the color of each pigment. So if you have three types of the cones, like neurotypical people, then around the fovea at the center of the your fixation, there is no cones that are sensitive to the blue wavelengths, short wavelengths. Okay. On the other hand, if you have only one type of the cone for the red and green, it's called deuteronomats. They all have only green sensitive or mid-length wavelength cone. And again, blue short wavelength cone is separated and sparse in the periphery. So that's the kind of physiological fact, okay? But it's really weird, isn't it? Who doesn't experience any blueness at the fovea? Isn't it hard to believe? Okay, so to see the way your blue phobia is, blue coneless phobia is, I'm going to show you the demo, and during this demonstration, if it's possible for you to make the room darker, that would be probably better, and then also make the screen bright. That's probably also better. And then fixate and don't move your eyes from this, central circle where I'm showing this, red thing right now. Okay. I'm just going to replace this and put the mouse cursor where, I want you to fixate in the next demo. And then let's measure for 40 seconds or so. Don't move your eyes and don't blink. Okay. That's important. Ready? Are you ready to start this demo? Hard to see. Okay. All right. All right. Let's go. Look at the center. Okay. 10 more seconds. 5, 4, 3, 2, 1, 0. Okay, I hope you saw some kind of after image. Did you see after image? Yes. Yes. And what I hope you saw was something like this, like very, very center of the after image was slightly brighter than the others. Okay, one key you saw it. That's great. Did any of you see this kind of two types of the level of brightness in the after image? No? You only notice one. Probably if you move your eyes a little bit, then it may not be able to see this kind of two types of the structure. But if you do it again, maybe during the video or using slides, and then look at this for 40 seconds or so, then hopefully the fatigue of your photoreceptors with respect to this particular wavelengths, because the with or without short wavelengths cones are different at the very center of the fovea versus elsewhere, you will see something like this. That's the point. But here, so if you're like me, this is a point where we don't have a blue cones. Okay, but it's very weird, isn't it? Because we see blueness here. So why is it possible to see blue here? Isn't it weird? Do you have any suggestion why this could be the case? You can either speak up or type. Maybe difficult to do. And in fact, if you can completely explain this, it is in fact almost like a paper or quite a novel theory. So I'll just leave this here because I just wanted to embed all these kind of questions to you rather than answer. Okay. So the next question is that if this is a case, all right. So as a scientist, what we want to do is not only to stop with this phenomenological observation that okay, we have this corresponding lack of the blue cone at the fovea as a after image phenomenology, but also we want to make it like a data that other scientists can also replicate and understand and believe. So how can we test this in an objective way? That's a question. So one of my postdocs, Ariel Zelezniko Johnston, has done the following experiment. And I'll give you the hint to you guys how to address this one, okay? So first, as a first stage, what Ariel did was to calibrate the luminance between the blue and green. So both green and blue, when presented like this, color wheel, it flickered between the blue and green, and then minimized its flicker so that it look luminance wise, equally bright. And then after that, what he did was to present these two patches or different types of the different levels of blue and green, two at the same time on the display, like this way, okay? Both at 1 degree from the fovea. And by the way, okay, so 1 degree from the fovea, very briefly, like just 500 milliseconds. And then after that, Ariel asked subjects to rate the similarity between these two colors from 0 to 7. If it's very similar like this, but it's not identical, as you can see, then you might say 5 or 4. And if it's identical, you might say maybe 0. It's identical. And then if it's definitely green and blue, then you might say 7. Okay? And then if you do this kind of experiment, what you find is the following. So if presented at the with respect to a blue and green shades here, okay, one patch at the 1 degree and another patch at 1 degree, then all these similar color pattern, green green or green green, and then blue blue, light blue, they resulted in the dissimilarity of 0 or 1. Okay, this is presented as a level of the dissimilarity. So 0 means it's similar. Okay, and then when presented with a blue and then green, then it's reported as 7 or 6. It's dissimilar. Make sense? So what this means is that when you present two things at the same time, then people can report the similarity reliably, and the diagonal is reported as a similar when two things are presented at the same time. And then when he also did that with a green and red pair, then he saw this type of the things. Again, blue and red, green and red are equated in terms of luminance here. And then you see that the diagonal is similar rating, and then off diagonal is dissimilar. So here's the question: what do you think would be the necessary experiment to prove that there is no blue sensitive cones at the dead fovea at the fixation? This experiment itself doesn't prove that we don't have a short wavelength blue cone at the fovea, but with another just a little bit change of the experiment, we can prove that. Can anybody suggest that? Is it too difficult? This is the kind of thing that I want you to think in the class, and also all the projects in the final project. This is something that no other people have done before, presumably. So I'll just give you one more hint again. Okay, so the area of the eye that doesn't have this blue cone is only 0.33 degree. Okay, so it's very small. It's roughly like 1/3 of your thumbnail at the arm's length. So that means that this experiment showing things at 1 degree from the fovea is not enough, in fact. So this is 1 degree, and it's very close to the fovea, but it's not close enough to detect this, blueless area. So in the end, what Ariel needed to do was to show the stimulus, comparison stimulus at the dead fovea. That's the answer. So I'll just erase others. Here you see, it may be a bit too small to see, but this is a place, actual place where you are looking at. And then he presented this, small stimulus over there briefly at the same duration. Okay. Then what happened was that this pattern of the result. So if it's blue to green gradation, if it's a blue to green gradation and then blue to green gradation, when presented at the fovea with a very small stimulus and very short duration, then whether it's presented as a green or blue, with respect to green, the similarity looked more or less the same. And then blue to green to blue is also the same, more or less the same. So this means that, we can't really discriminate between blue and green at the phobia. On the other hand, when you present the small thing as green to red, then you see basically the same kind of structure here. So green to red is totally visible within the phobia, dead phobia, but not for the blue and green. Is that clear? So this is a kind of how the science works. You have a control experiment here where you establish that a 1 degree patch can be discriminated in terms of similarity, but when one of them is brought to the phobia, then you cannot start to see under the report. Okay, so that's how we demonstrate that at the 0 degree, we don't have a blue sensitive cone, and we don't have a blue phenomenology. But when presented for a longer duration, then probably you make a lots of small eye movements, and that's the reason why you can see blue. And also there is some kind of filling in from outside and so on, and that also helps to see things clearly in the phobia, around the phobia in the blue. Okay, so is there any questions so far? Fine. Okay, then let's move back to this. So in summary, retina in the eye is a sheet-like structure. And then from the retina, information is sent to the brain via lateral geniculate nucleus that I'm going to talk about next week, and other structures. And while short wavelength sensitive cones are absent in the central fovea, we usually see blueness there. Why? That's again, not exactly known in the science, but the likely scenario is that there is a filling in from the outside, and also there is some kind of compensatory mechanism in the brain. And do we have any other example of unknown phenomenology induced by the structure of the eye? That's a question in the next. So far, fine, I guess. Then as an example of this unknown phenomenology to you, I just wanted to show this image. Here again, I want you to fixate at the center here. And then try not to blink, try not to move your eyes, and then what do you see? Can you report your phenomenology in chat? Do you see this visual display? Right now, it's kind of green things probably moving around, no? Or is it too faint for your display? The violet phase, yes. And single green one is left. Do other people also agree with this phenomenology? Agree. Okay. Yep. So what's happening here is quite weird, in fact. If you stop this, the pink circle is gradually disappearing and the small green circle is moving. Yeah, great. So pretty much everybody then agreed that what you see consciously is what's not there. What I mean is that if you stop this display, maybe in the video, or you can actually, I can take a screenshot here. Then you see this is a screenshot I made, and then you see that only one part is missing in terms of pink, right? And then across a GIF image, it's just circling around many different kinds of frames around. And then what happens is that it's not only the pink circle phase, but it's also replaced with the green thing, and the green thing itself is moving. So you don't see pink, but you see green, and only one, and it's moving. So this is the exact kind of opposite of what's physically there. What you're consciously seeing is the opposite of the physical reality. And this is quite a complex kind of phenomenon, in fact. But it also needs to be explained in any of the theories of consciousness. And definitely one factor is called due to the after image. The pink's opposite is green, in fact, and that's the reason why you see green. And then this is something that we will discuss in the several weeks later, that attention and consciousness with respect to after image goes in the opposite way. So the fact that each frame changes its position attracts your attention to there. And then this kind of faint image, the more you pay attention to it, it fades from your consciousness. And that's why that attended location starts to be more clearly green and also less pink. Okay. And this complex kind of interaction between attention and consciousness and its opposite effect gives rise to this phenomenon called the lilac chaser, and that's the topic for the topic to think in the probably in your mind. Attention and the consciousness is not the one thing; it's another thing that requires you to think about or doubt the common sense. Okay. So let's go to the next topic. What are the properties of the retina in the foveal and the peripheral areas? Do you see color in the periphery? So this is the third component in today's topic. One is a blue sensitive cone, lack of it in the dead fovea, and second one is that right now what you saw, because of the attention and consciousness interaction and also after image. There can be a situation where you see is what's not there in the world. And the third one is about the phenomenology of the color in the periphery. And this goes with quite a bit of the against the textbook explanation of the color and consciousness. So the fovea versus periphery. First, let's go first. Density of the cones, the photoreceptors that are responsible for color vision is highest at the fovea and drops quickly into the periphery. Have you ever heard of this fact in other classes or courses, or maybe in the book? Is this something that you have never heard before? Okay, maybe I'll just ask it in the 3AFC later. Okay, and then it's an important structure and concepts. Again, fovea and the periphery, and so the eccentricity is the sort of degree or distance from the fovea. And then I want you to examine what you see in the periphery. And then can you describe your experience at the periphery? Okay. So far I've been telling you a couple of times that thumbnail at the arm's length is roughly 1.5 degree visual angle. So I'll just demonstrate how you see it. So with this display, I think you probably can see my face better. But what I want you to do is to extend your arm like this, and then place it in front of you. Okay. And then because the proportion of the arm's length and the thumbnail is more or less constant across any people, what you end up in seeing is that mostly similar size of the objects for everybody. And that is scaled with respect to your body size. So it's a useful thing to remember. And I might ask you also about this in our e-assessment, is that the size of the thumbnail width is roughly like 1.5 degree, okay, at arm's length. And one third of this size. So no. 1/5, right? 10% of this is a 0.15 degree, and then 20% of this. So 1/5 of the nail, roughly like this way, is the part that you don't have a short blue wavelength. So if you paint with your manicure, maybe blue manicure, and then you probably won't be able to see it whether it's a blue or green. So maybe you can actually try that on the right side, right thumbnail to be green and the left thumbnail to be blue or something, and then paint it in a very small way, and then see or enjoy why you can't see the green and blue over there. And so anyway, this area, roughly like 1.5 degree, is where you can see the things at the highest resolution. So in terms of the density of the cones and the rods, this is a very famous figure that you see in many of the psychology books and also physiology, where eccentricity, that's a sort of distance from the fovea. Okay, so here at the point of fixation, that's about 0 degree. And then based on this fact that the thumbnail is roughly 1.5 degree, you can imagine that the edge of the display, computer display, if you have your thumbnail at the finger, at the arm's length, and then go to the at the edge of the display, then you'll see that it's roughly like 10 to 20 degree. That's your computer display size. Okay. And the fact is, the density of the cones responsible for color experience declines significantly. So the peak is here. Okay. Peak is at the fovea, and then it declines really quite a bit. And then by the time it's going around 10 degree, and this part becomes 0, by the way. And that's because of the structure called blind spot, which I may talk about it later. But somewhere around the display, edge of the display, the density of the cones goes almost like minimum. Okay, from this, what can you expect about your color phenomenology? Okay, so this is true for both short wavelengths and the middle wavelengths and the long wavelengths. So that means that the blue, red, and the green sensitive cones goes in a very low density. What do you expect to see if you show some stimulus, let's say around here, and then project it into this area of the eye? Okay, let's do the poll. Launch. Okay, so the question is that the A, now a question option is that if you present something at periphery, outside of the display area, something around here, and then hit on around this, area where your cones are very low in density, you don't see much color. So first is no color, and then B is that yes, I still see color. It's about question of your phenomenology. Which one is your experience? As I said, this is roughly the display size, and that goes 10 to 20 degrees. And so if you present something outside of the display, you can check that. And all right, so most of you already responded. Okay, now it's roughly like 25 minutes again. So let's take a 5-minute break, and we'll come back from this.